So, today we are going to start sequences and series. First of all, what is a sequence? A sequence of real number is a function defined on the set of real numbers whose range is contained in the set of real numbers. So, if I say x is a function from n to r, so x is a mapping from the natural numbers to the real numbers, and range of x, that is r of x, is a subset. Remember, it is a subset. Oh, sorry, I wrote equals to. It will be a subset. It is a subset of real numbers, or a set of real numbers where it is range of x. Then we can say that x is a sequence. So this is the way a function is identified as a sequence. So remember, the domain should be natural. So where n is the domain. Remember this is one of the most important things, that the domain should be natural, then x is a sequence, and the range should be a subset of R. So that was the basic definition of a sequence. Now, okay, where should I write? Okay, okay, light here. Uh, it is denoted. It is denoted by. So you can write sequence in a short way. These are the shorthand to write sequence. It denoted by x. You could write in caps, this is set, and then x in subscript you write n, and these things needs to be in parentheses. So these are one of the shorthands, or you can even write it in curly braces x of n in subscript. Then again in subscript you can write n belongs to natural. So these are the ways you can actually write a shorthand. The shorthands for writing sequences. What this actually means? It actually means a set of x1, a set of real numbers which contains x1, then x2, then x3, and so on till infinity. Why infinity? Because the set of natural numbers is infinite, is uncountable. As the domain is uncountable, so there are going to be uncountable terms in x also. So I'm going to give you some examples which will make things a lot more clear. So example, let's go over some few basic things. Let's say the first sequence which I'm going to talk about is this one. 2, then 2 to the power 2. Okay, that's very bad. 2 to the power 2. We'll write it down again. 2 to the power 2, then 2 to the power 3. Then it goes on and on. And you know it will go on to infinity only. Then this is actually a GP. Then the next one is, suppose this one. So it is root 1, then root 2, then root 3. So as you can see, the domain is natural because I'm giving the function to be root n. So my variable over here is n, not the whole stuff, but the range is in R. And if I want to define for the first time, it will be 2 to the power n. And it goes on like that. These were some basic things. I think there should not be any trouble understanding this because these were all basics. Now we come out to how to define a sequence. So how will you define a sequence? There are basically two ways. You can give a expression for the nth term. What that means is you can say that x of n is equal to something, say, over, let's say 2 times n for all n belonging to natural. So this is a sequence of even numbers actually. So if I write x is equal to x of n, remember shorthand for writing sequences, then it is a set of it will contain the 2, then 4, then 6. So as you, it is a set of even numbers, so it goes on to infinity. And then recursive way. What is recursive way? In recursive way, we define some preceding terms and then define the nth terms in terms of the preceding terms. If I want to write this expression in recursive way, let's say x of 1 is equals to 2. So I'm supposing, so I define the preceding term, x of 1 equals to 2. Now I want to have x of n equals to 2 to the power n. What should I do? Well, it's actually quite simple. You can just define x of n. Now remember, x of n should be written in terms of its preceding terms. So you can write any terms. I will just define for x of n on the basis of x of n minus 1. So I will write x of n equals to x of n minus 1 plus 2. Now, look at it carefully. Where should n start from? If n is equals to 1, then x of 0 it will come. Then x of 0 is undefined because I don't know what is x of 0. So n should start, or n should be greater than 1 for x of n to satisfy this condition. And obviously it belongs to natural. If you check these conditions and then write the value of x of 2, x of 2 will actually come out to be x of 1 plus 2, which is 4. 2 plus 2 is 4. Then we want to write x of 3, it will be x of 2 plus 2, which will be 4 plus 2 equals to 6. And then if you continue like this, look at the pattern, you will find that x of n, by the formula it is x of n minus 1 plus 2. And if you look at the pattern there, it actually goes on like that. Then x of 2 is 4, so it's 2 times 2. Then x of 3 is 6, it's 2 times 3. So x of n should be like that. It should be 2 times n minus 1. Then plus 2, it will make it 2n. So we wanted this thing only and we came back to it. So we found that x of n is equal to 2n, which we wanted to define in recursive way. If I define a sequence y, which is x of n, and now the x are this x over here, which I define in the recursive way. So then you compare these two sets, you will get y is equals to x. This simple way of defining sets by recursive way or giving the expression for the nth time. So now we are going to see limit of a sequence. A sequence x equals to x of n in R is said to converge to lambda belonging to R if and only if for all epsilon greater than 0 there exists k of epsilon belonging to natural. Now k depends upon the choice of epsilon, so I have written k as a function of epsilon. Then we have if for all n greater than equals to k of epsilon, x of n satisfy x of n minus lambda is less than epsilon. This is a condition for convergence of a sequence. And all this thing is actually equivalent to finding the limit. So it is actually equivalent to finding the limit as n tends to infinity. So as n tends to infinity, x of n. What is the value of x of n as n tends to infinity? If this quantity is finite, then we can say the sequence given by x of n is convergent to whatever that finite quantity is. So this is basic definition of limit of a sequence. Note that epsilon is arbitrary, k depends upon epsilon, and lambda is finite. Now if I write the expression x of n minus lambda is less than epsilon, which is a given condition for convergence, then if I remove the mod, what I get is minus epsilon is less than x of n minus lambda, which is again less than epsilon. Now if I add lambda to all the sides, I get lambda minus epsilon is less than x of n, which is again less than lambda plus epsilon. Now we have epsilon greater than 0. So if we can choose epsilon to be very close to 0, what will we get? We can actually choose epsilon to be very close to 0. And again, remember one thing, if I choose epsilon to be very close to 0, the value of k of epsilon would be very high. I repeat, if I choose k of epsilon to be very close to 0, the value of k of epsilon will be very high. I will show it to you with an example. Well, but first of all, let us continue. If we choose epsilon to be very close to 0, we get lambda is less than x of n, which is further less than lambda. But what does this mean? A quantity is bounded by the same quantity on both sides. So, can we say that x of n it starts to behave as lambda when n is greater than k of epsilon? Because see, this thing is completely trapped under two lambdas, so we can say from this condition we see we see x of n it behaves as lambda. It behaves as lambda. uh, okay, that was I should write the lambda a little more clear. So we see that x of n it behaves as lambda. Now, it's a very interesting condition, and also remember that this will be true if epsilon is very close to 0, that is if epsilon tends to 0 or epsilon is very close to 0. But it is not equal to 0 obviously, because epsilon is always greater than 0. It is a positive quantity. So we find that x should behave as lambda, and this is what we mean by convergence actually. So I'm going to give you an example which will make things a lot more simple. So example, suppose I've got this sequence that where x of n is given by 1 by 2 times n. So this is a decreasing sequence because as n increases the value of xn decreases for all n belonging to natural. Then limit n tends to infinity. Remember the convergence, it is just equivalent to finding limit n tends to infinity x of n, which comes out to be 0, because we have got an infinite quantity and then we are doing 1 by infinity, and which is actually 0, because a finite quantity by infinite quantity is 0. So in this case we have lambda, which is lambda the convergence point to be 0. So if I go back to my initial condition that x of n minus lambda should be less than epsilon, what I get is I'm writing it down again. So x of n minus lambda is less than epsilon. Now lambda is equal to 0, and obviously don't forget that to write for all n belonging to k of epsilon, because you will just find out from this example only why k of epsilon is important. So we get x of n is less than epsilon. Now let us set epsilon to be 1 by 32. Now this is a positive quantity, and we know we can choose epsilon arbitrarily. So this all the things are valid till now. And if I write the x of n according to definition, which is 2 times n, I get 1 by 2 times n is less than 1 by 32, which is actually 1 by 2 into 16. So if I cancel out the 2 on both sides, I get n to be greater than 16. So what is n over here? It is actually that k of epsilon, because remember we showed that x of n will satisfy that given condition if n is greater than equals to k of epsilon. So in this case what we found out is k of epsilon should be greater than 16. Now let us set epsilon to be 1 by let's say 512. So another bigger quantity, so now epsilon becomes a lot more small. So we can write 1 by 2 times n is less than 2 times 256, which is equal to 512. Cancelling out the 2's again, doing the same thing, same calculation, we get n is greater than 256. Do you notice something? Yes, the value of k of epsilon increases a lot. It is actually now 16 square. Yeah. Oh, sorry, I wrote equals to. It should be k of epsilon should be greater than 256. So, as you see, as we go on decreasing epsilon, the value of k of epsilon increases. So, as epsilon approaches 0, k of epsilon increases. It is quite evident from the example we showed over here. So, as I told you earlier, if we choose epsilon to be very close to 0, we need to have a very large value of k of epsilon. So, coming back to the notes, remember this thing, epsilon is arbitrary and k, that is the k of epsilon, it depends upon the choice of epsilon. It always depends upon the choice of epsilon, and lambda is a finite real number. So all these conditions are true, then we can say that the sequence x converges. So these are the conditions for convergence of a sequence, and